Hi, everybody. This is a biology class, but before we can talk about how life works, we should probably start with what life is made of. And so, if we were going to look at a periodic table, that would be pretty overwhelming, so let's simplify it down. Life is not made of that many elements in general, and so here they are. And here's our advanced technology, the whiteboard. Now, the elements you are composed of are primarily found here, and there aren't that many. We're starting with these here: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and sodium, calcium, and potassium. Now, if you're wondering about the color coding, we can start with the ones at the bottom. These three right here are generally found in ion or salt form. Sodium, calcium, and potassium are going to be dissolved in your body fluids. Okay, so we're not going to be talking about them a whole lot when it comes to the makeup of your body, but most of the molecules of your body are actually composed of the top five there. And so that's carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Oh, I guess that's six. So that's what we're made of elementally. And if you're wondering, how do I remember those? Because there's so many there. Oh, so I've got a really stupid mnemonic for you. So if you're running low on some sort of thing that you're made of and you need to replenish it, what you need to do is chomp a snack. Yeah, I told you it was stupid, but you're gonna remember it because it's that stupid. So just chomp a snack and you'll be able to replenish what you are made of, at least elementally. So, all right, so these are the elements you're made of, but how are they like formed into the molecules you're composed of? Well, if you take the top two, you generally can make a lipid. If you take the top three, you can make a carbohydrate. Top four, you can make a protein. Top five, you can generally make nucleic acids. All right, so what are you actually made up of in the molecular manner? All right, here we go. So you are composed of, in order, this is actually an order. Um, I think you already know this, mostly water. Okay, that's 65+% of you by mass. It changes depending on your level of hydration, but that's most of what you are. Now, if you got rid of the water, you took a person, put them in a blender, and then desiccated the remains. Don't think about that too much. What you'd be left with is mostly protein. Okay, honestly, you are mostly protein. In fact, what you're looking at when you look at me, when you look at anybody, is protein. The protein in the hair, the protein in the skin, almost all of what you see is protein. Now, under the surface, there's definitely a bunch of lipids. And so that's less than half of your dry mass are lipids. Again, most of you, protein, lipids next up. Now, way, way down the list, down from the like 50+% and 30+% of the lipids, we're going down to like minerals. Now we're down to like 4% of your dry mass. These are the calcium, magnesium, phosphate salts in your bones, things like that, plus the ones that are dissolved in your body fluids. Below that, you're still going to have to go pretty far down. We're down to like 1.5% of your dry mass. We're down to RNA. Below that, the carbohydrates, which are always the first ones listed in textbooks for no apparent reason. And DNA, there's so little of it, it doesn't even show up. We're talking about 0.1% of your dry mass. So there's not really much to talk about. So what we're going to start with, though, what we're going to start with is the water. And it's important because it's the environment for everything else in your body. So how are you putting these like atoms together to form these molecules? Well, you aren't putting them together generally. You're honestly, consuming them for the most part. So back to our element list. How are these put together in nature in general? Well, anything down at the bottom, and we're talking about bonding here. In terms of bonds, well, the ions may form ionic bonds and form salts, right? You may be aware of that. Honestly, when it comes to biology, ionic bonds are not the most important things. We talk about them a lot in a chemistry class, in an inorganic chemistry class. In our bodies, there's so much water that most salts are dissolved, right? So these are just ions, pure ions, and there aren't many ionic bonds that we need to really think about strongly, except within larger molecules like proteins. We'll get to that later. So there are going to be two categories of bonds that you really need to think about. So up here, the categories of bonds that you're going to find between these atoms are generally going to be bonds where they're sharing electrons, and those are your covalent bonds. Okay, so anytime you're sharing electrons between a carbon and a carbon, carbon and a hydrogen, hydrogen and oxygen, oxygen and nitrogen, nitrogen and hydrogen, et cetera, those are going to be covalent bonds where they're sharing electrons. And then the other bond we're going to end up talking about a whole lot are hydrogen bonds. But hold on to that for now. So we're going to start with water. So here we go. There's water, oxygen flanked with 2 hydrogens, and there's all this other fancy stuff written around the edges there. And it's, it's actually quite different from these other 2 molecules shown up here. And there's a reason that I'll get to. Now, if you take 2 hydrogens and bond them, covalently, yes, you get H2. And the most important thing to realize about those 2 atoms in the hydrogen molecule, that they each are identical, which means that they each have an equal pull for the electrons they're sharing, so there's no imbalance between the 2 hydrogens. The same thing is true of O2. The 2 oxygens have equal electronegativity. If you don't remember that term, it's simply put their pull for electrons, and they're equivalent, and so you're not going to have any imbalance. Now, when it comes to oxygen and hydrogen, though, they are different from one another. The oxygen is relatively massive. And so what you have is the oxygen is going to be a whole lot more electronegative. It has 8 protons compared to the 1 per hydrogen. And so the electrons that are found shared between the oxygen and the hydrogens are actually going to be pulled more towards the oxygen. Now, the reason that's important is, again, the imbalance. Electrons are negatively charged, and so if they're negatively charged and they're more in this direction, well, that means this guy over here is going to be a little less negative. And translation, a little less negative means a little bit positive. And so that's why you have these plus signs, these minus signs up here. These 2 orbitals up here are going to be a little bit negative, and these 2 down here will be a little bit positive. If you're wondering what that squiggle is, it's a lowercase delta, the Greek letter. And that indicates that it's not a full charge. We're not talking about ions here. We're talking about a molecule of water that is overall neutral, but has little bits of charge imbalance. And so time for toys. So I've got toys, and so I'm going to play with them. I'm sorry you don't have these. I do. And, nerd fun, here it comes. This is water. And it has 2 white things and 1 red thing. And I should probably ask a question here, but I think you know which one is which. Now, if I take 2 water molecules, you may remember the red one is a little bit negative, and the white one is a little bit positive relatively. Overall charge of 0, right? But little imbalanced. So, a little positive, little negative areas relatively. So if you take water molecules, they do weird things like that. So they have minor levels of attraction. And right there, this is not an ionic bond. These are minor charges, charge differences. Polarity is the term for it, by way of a hydrogen. And so this, being charge imbalanced, though 0, neutral, is polar. This is also charge imbalanced, neutral, but polar. And so because of those charge imbalances, that polarity, they can stick a little bit. Not a strong bond. This is called a hydrogen bond. Very weak bond. In fact, I could break 1 trillion hydrogen bonds anytime I wanted to. I was going to swirl some water here, but I forgot my cup. Well, so yeah, you can break hydrogen bonds, no problem. Any sort of force will do it. A little bit of heat, a little bit of motion is plenty enough to break bonds, hydrogen bonds. That being said, when you get water together, there are lots and lots of hydrogen bonds. You get a bunch of this stuff, and they might be breaking and forming regularly over and over and over and over again. And to break them all, take this thing and break all the bonds, that would take a lot of energy, right? You'd have to move them really fast. So that's why watched pot never boils, that saying. You're trying to basically break every single hydrogen bond so these can separate away from each other and turn into a gas. The reverse also requires the removal of a lot of heat. And so if you want to slow this stuff down an incredible amount, you can form the maximal number of hydrogen bonds. That's when every single water molecule is forming 4 bonds, 4 hydrogen bonds, using their 4 partial charges. And that's when you get ice, perfect crystal. So that's the basics of water. And so this is a polar molecule. It forms these sort of minor electrostatic charge-based interactions. But again, it's a neutral molecule, but it's polar, just imbalanced. And so that leads to things like surface tension and a high specific heat. And the real reason this is important is because of what interacts with the stuff. So this is a polar molecule. Anything that's polar, if it's small enough, will dissolve. So most of the stuff in your body that we're going to talk about is going to be polar and will dissolve with this. So what we're going to really talk about, though, in this unit, primarily proteins. And the proteins are massive, and they're complex in shape and properties, and regions that are more polar versus less polar, charged versus uncharged. That's going to lead to the shapes of these proteins, and that's what makes you who you are. Okay, so that's the intro to water and their bonding and the different properties of it. Next time, we'll talk about proteins and really get into the nitty gritty of what you, other than water, are really built with. Thank you. I'll see you next time. Bye.